Hi there, and welcome to this lecture on convergent and transform boundaries. Basically, in this lecture, we're going to learn about both the features and the type of movements we see with the plates as in relation to these type of boundaries. Convergent boundaries are famous for producing things like dangerous tsunami, very large earthquakes, and volcanism. In fact, some of the most violent volcanoes form at a convergent boundary. So we're going to spend the first part of this lecture learning about that. And then in the last part, a much quicker part of the lecture actually, we're going to take a look at our own type of plate boundary here in the Bay Area called transform plate boundaries. And if you're in my geology sections, you'll actually learn about transform boundaries in regards to earthquakes later on in the term. So with that being said, let's go ahead and get started. Let's go to the next slide. So for the convergent plate boundaries, there's actually three different types. There are two of them that are subduction zones and one that is not, although the reason for the convergence actually has to do with a subduction zone. Once two continents are in contact with one another, there is no active subduction at that point. So we'll talk about that one after we talk about the subduction zone type boundaries, which are ocean-continent and ocean-ocean. So as far as features are concerned, I'm going to use a block diagram to discuss and show you the relative differences spatially as far as these features are concerned. And I'm hoping that these features will make a lot more sense going through it that way. After we're done doing that, we'll have a review slide that actually gets into the differences between the two subduction zones. You're going to find that the two subduction zone boundaries are going to be very similar to one another, but there are a few important differences that you should keep in mind for the exam, obviously. So let's go ahead and go to the next slide and start discussing these boundaries in more detail. So we'll start with ocean-continent convergence. And the first thing I want to discuss is why we have subduction to begin with. For ocean-continent convergence, it has to do with the materials that are coming in contact with one another at the boundary. So the boundary in this diagram would be right here if you look at my cursor there. That's where the two plates are meeting, the oceanic lithosphere and the continental lithosphere. They are meeting right there at the surface, and that would be considered the boundary. So the reason for subduction has to always do with density difference, and the density difference in this combination has to do with the composition of the material. As we learned in an earlier lecture, continental crust is very felsic and also the least dense of all the materials, whereas oceanic crust is mafic and more dense. And so when you put the lithospheres together, overall the oceanic crust with the ultramafic mantle underneath making up the entire lithosphere is going to subduct under the more buoyant continental lithosphere. So that's the reason for subduction. You'll notice right at the meeting point between the two plates we have what's called a trench. That's very counterintuitive, much like the divergent boundary having a ridge. This is also counterintuitive as well, because you think of a collision, you would think big mountains would form as a result of that. And actually that is true when we talk about continent-continent convergence in a little while. However, when we're talking about ocean-continent convergence, what ends up happening, if you follow my cursor again, is as this plate, this oceanic lithosphere is subducting, it actually takes this continental plate here, continental lithosphere, and drags it down as such. And it's not really shown very well in this particular block diagram, but that's what's going on. As the oceanic lithosphere is subducting, it's dragging and pulling down the continental lithosphere a bit, and that actually creates the trench that trench is not insignificant either. It's actually up to 30,000 feet deep in places. In other words, you could fit our tallest mountain in the world, Mount Everest, into it with plenty of room to spare. That's how deep these trenches are. So it's not an insignificant feature to talk about, much like the mid-ocean ridges at divergent boundaries are 6 to 12,000 feet above the seafloor. Those aren't insignificant features either. At first glance and not knowing the whole system, very not intuitive as far as the features are concerned. But once you start to understand the system and what's going on, it actually makes perfect sense. So hopefully this trench in its location that it is in makes perfect sense as well. And in fact, you could look at a map of trenches across the world. If you have a world map and the trenches are actually mapped out on them, you can also infer that subduction zone is also there as well, because that's what trenches and how trenches are formed is only through subduction. All right, so another feature that is shown in this block diagram are obviously the volcanoes. As the oceanic lithosphere subducts into the asthenosphere, it brings water down with it. And that water, once it gets under extreme pressure, starts to act on the lithosphere and the asthenosphere in particular. Right there, you'll notice where the melting's happening. It's actually happening in the asthenosphere. The asthenosphere is already close to its melting point near the surface, and so adding water actually lowers that melting point to make it melt. And the water is coming from none other than our ocean, and as the plate subducts, it brings water down with it, because this rock is all got cracks all through it, so it easily brings water down. And then that water interacts with the asthenosphere, causing melting. And then that melt, being less dense in the surrounding rock, rises up to create the volcanoes that you see here. So for an ocean-continent convergent boundary, we actually call the volcanic arc a continental volcanic arc. And the reason we call it that is because the volcanoes will always be on the continents. Hopefully you could see with this block diagram, the volcanoes will never be on the plate boundary. They will never be on the plate boundary. They're always going to be away from the boundary because melting isn't going to happen near the surface. You need that oceanic lithosphere and its water to come down to where the asthenosphere is to cause it to melt a little bit. So that's going to happen at depth, and it's going to happen under the continents. And the nearest subduction zone like this, ocean continent subduction zone, is actually north of us in northernmost California, Oregon, and Washington State, in a place called the Cascade subduction zone. And Mount Lassen, Mount Shasta in California are both a part of this. And if you've been to those two locations, you know they're not even sitting on the beach. They're sitting well inland in California. So that gives you kind of a better scale, besides a block diagram, to consider as far as where these volcanoes actually start to form underneath the continent. It's not right at the beach. It's actually still quite a ways inland. You can go to the coastline of northernmost California, and you would never see a volcano up there. That'd be Eureka, Fortuna, places like that. Okay, so the volcanic arc is on the continents always. And then, of course, you would never see the volcanoes sitting on the oceanic lithosphere in this situation, in ocean-continent convergence, because that would require the subduction zone to come down at an angle and then kind of suddenly whip around this way. That isn't going to happen, obviously, for a lot of reasons regarding the laws of physics, first and foremost. So keep that in mind as well. All right, so the last thing I want to talk about, and is not shown in this diagram specifically, is the earthquakes. As we talked about in the divergent margin, we consider earthquakes to be at depths between 0 and 100 kilometers approximately, because earthquakes only happen in the lithosphere. anything deeper as far as an earthquake is concerned is going to be at a subduction zone, because that is the only location where lithosphere is shoved underneath other lithosphere, and therefore underneath or deeper than 100 kilometers. And so you can see in this block diagram they show about the 100-kilometer level there. Just a little thicker at the continents, a little thinner at the oceans, but average about 100 kilometers. But look at this oceanic lithosphere subducting. It's going down pretty far at depth. So we can get earthquakes all along this zone. And in fact, if we plot earthquake epicenters, we can, and just look at that along with their depth, we can actually tell where subduction zones are in the world just because of the depth of the earthquake. So we'll take a look at that in a couple of slides in just a little bit. All right, so I think that covers most of what I want to talk about with ocean-continent convergence. Let's go ahead now and go to the next slide and look at ocean-ocean convergence. Now, thankfully, as far as studying purposes are concerned, most of the features are pretty much the same, but there are a few key differences. And the first key difference that I want to go over with you now is the reason for subduction. We are dealing with two oceanic lithospheres, obviously, and so the composition is going to be the same, basically mafic and ultramafic. So composition cannot be the reason for subduction in this case, like it was for ocean-continent convergence. So what is the difference here? Now, keep in mind the density difference is present. You wouldn't get subduction unless there was a density difference between these two lithospheres. So aside from composition, which obviously isn't the reason for density difference here, what would be? Give you a second to think about that. What is causing the density difference between these two lithospheric plates? I'll give you a second to think about it. All right, if you're still thinking, go ahead and hit pause, and we'll go ahead and go through the answer. The answer is temperature. Remember, in the divergent boundary section lecture, we actually talked about the oceanic lithosphere being created through seafloor spreading and volcanism. And so it goes as far as that's concerned, basically temperature, the newer the material is, the warmer the material is, because it was created through high heat flow. And the older the material is, the colder it's going to be. And remember, the hotter a substance is, the less dense it is as well. So what you're looking at in this block diagram is the oceanic lithosphere that's not subducting is actually the newer lithosphere. And the subducting oceanic lithosphere is the more dense, colder, and older lithosphere. So oceanic lithosphere that is new and warm will be always the overriding plate. And the older and colder oceanic lithosphere is always going to be more dense and be the subducting plate. So basically, as far as the features are concerned, we still have a trench. If you follow my cursor, we still have the trench right on the boundary. And the trench is about the only difference between the trench of an ocean-ocean convergent boundary and an ocean-continent convergent boundary has to do with the location relative to a continent. For ocean-ocean convergence, there isn't really a continent close by, and continents love to shed their sediment into the ocean via rivers. And an ocean-continent convergent boundary, the trench being right next to the continent, it gets filled in with sediment a lot more than an ocean-ocean convergent boundary. So the trenches, in other words, tend to be deeper. In fact, the deepest trench, the Mariana Trench in the Western Pacific, is actually over 30,000 feet deep. That's the one you can fit Mount Everest into, and it is an ocean-ocean convergent boundary. Now, that's not to say that ocean-continent trenches are not deep. They are. They can get upwards of 25,000 feet deep or so. Some of them are actually filled up entirely. The trench that is off the coast of Northern California, Oregon, and Washington is being filled up consistently and constantly by the Columbia River that actually sheds quite a bit of sediment off of our continent. So much so that it's filled the trench entirely. So if you were to look at the ocean floor off the coast of California, northernmost California, Oregon, and Washington, you wouldn't see one there because the Columbia River just likes to dump sediment constantly into that trench. All right, the other thing is that you see here is the volcanic island arc. The difference, that's the other key difference actually, the volcanic arc is going to be on ocean lithosphere because that's all you're dealing with here is ocean lithosphere. And so therefore the volcanoes will be islands instead of being on the continent. And then you can see clearly why here. The reason for melting is the same. It's just going to, the volcanoes are just going to manifest themselves as islands instead of being on a continent. All right, the earthquake patterns are also the same in this situation. We're going to talk about that here in a moment. But first I want to go ahead and go to the trench map because I did put a trench map in here just so you could see all the trenches around the world and where they're located. Notice that they're mostly around the Pacific Rim. So get my cursor out here. So the Pacific Rim is this region right around the Pacific Ocean. And lots of trenches throughout here. We got the Indian Ocean as well with trench, and there's a couple in the Atlantic. But wherever you see an oceanic trench, you could be assured that subduction is happening there as well. And you don't see a trench, like I said, off the coast of Northern California, Oregon, and Washington because it's been filled up by the Columbia River that comes through. The Columbia River is located between the boundary of Oregon and Washington, if you're curious. Actually, that river is the boundary to those two states. The river is used that way up there. All right, let's go ahead and take a look at earthquakes. Let's go to the next slide. Now, as I said, we'll get into a lot of details regarding earthquakes in the module on that if you are in my geology classes. If you're in my oceanography class, we're not going to delve into earthquakes much aside from this lecture. So if you're interested in earthquakes, definitely take one of my geology classes and ask me about them, and I will help you out with letting you know where they're at and what time they're at and all that kind of stuff. So with that said, let's look at the earthquake epicenters here. And epicenters are always the map projection of the earthquake from depth. Earthquakes always happen at depth, some sort of depth, whether it be really shallow or really deep in the situation of a subduction zone. Subduction zones are the only places where you're going to get intermediate or deep earthquakes. And usually if I say deep earthquake, I'm also including the intermediate because we're not going to really talk about focal depth very much with earthquakes. So I usually just say if it's not in the zone where the lithosphere is thick, so if it's not within the 0 to 100 kilometer zone of the underneath the surface, it's going to be deep. So just keep that in mind. But you'll notice these are the shallow earthquakes where my cursor is spinning around in the blue dots there. And notice the green and red are going to be in the subductive slab below where the lithosphere is thick. Now notice how this is projected on the map. The shallow earthquakes are always going to be basically at the trench of a subduction zone. And notice on this map where the blue dots are situated at, right along the Japan trench. So we're using Japan as an example in this situation. And so just by looking at map view of epicenters and their projected focal depths, here's your intermediate and deep, we can actually tell the direction of subduction. The direction of subduction is going to be in that direction. The deep earthquakes are there, the deep ones are there. So we've got the shallow ones there. So that tells us subduction's happening basically in a westerly direction, excuse me. So like that. Now, where does that become very useful for looking at a world map? Well, let's go ahead and take a look. So there is our world map with the different color codes. Basically, the color codes here are the same except for intermediates given in yellow instead of green. But you can tell right away just by glancing at this map where the subduction zones sit, because you're only going to get the intermediate and deep earthquakes in a subduction zone setting. So obviously off the coast of South America, Central America, Alaska, Japan, Philippines, Indian Ocean, so on and so forth. You'll notice there's no deep earthquakes or intermediate earthquakes here, and that's kind of curious, but there is definitely subduction going on there. It's just at the span that this map was done in, which I think was over a 30-year period, there just really wasn't any deep earthquakes to plot for whatever reason there. But you can see that we have the intermediate deep in the Atlantic as well. You can even see a little bit right there and some right in here. And even though active subduction isn't happening in these locations now, there actually was subduction, and therefore a subductive slab is sitting there deep. So you can still get earthquakes along it even though the subductive slab isn't pushing down. So we'll take a look at how that works in just a little while. Okay, so let's go ahead now and go back to the original cross-sectional view. So I just wanted to come back to this so you could remember what those colors actually meant in difference. The deep earthquakes would plot there, the green there, and the blue right along the trench, and that's what you're seeing right there. All right, let's go ahead and go to the next slide. And this, even, it's a text heavy slide, but it's not really meant for anything other for you to go back and read later on to study for your exam. Just some of the key differences in terms of what these subduction zone features represent. So you can go ahead and pause and read through this on your own. I'm not going to belabor that now. And if you have any questions, let me know. All right, let's go ahead and go to the next slide and go through the last convergent type of boundary, continent-continent convergence. Now, as I said, you see an oceanic plate subducting here, but what's happened is this has collided. These two continental lithospheres have collided because of subduction. I'm going to come back to this slide in just a moment, but I want to tell you how we got to this position first and why this is just hanging here. And in fact, I should mention right now that if we were to animate this particular block diagram, you would see these mountains rising and this just hanging out, not moving at all. So with that said, let's go ahead and look at an example of how this works. Let's go to the next slide. And what you see here is two block diagrams before and after of basically our only continent-continent collision zone on the world today, India and Asia. And this is where Mount Everest, our tallest mountain range, is located. Let's talk about how this works. So before we had the collision, you'll notice we have the spreading center, mid-ocean ridge through here. And India was a tiny continental lithosphere that is basically riding on the plate on this side. And as divergence was happening here, India was basically being pushed toward Asia, and there was an intervening ocean basin before India collided with Asia, and this is that there. And here what you see is that intervening ocean basin subducting and creating the continental arc that you see depicted right here on Asia. Now, after some time has passed, India ended up colliding with Asia, and you'll see that the subductive slab is still there, but now it's halted, it's stuck, because now all the energy is being taken up in the collision of the two continents. But continental lithosphere is very buoyant, so you're not going to get one subducting underneath the other. Instead, what you're going to get is elevator up, and basically the Himalayas are growing at several centimeters per year. And as long as that divergent boundary keeps pushing India this way, these Himalayas are going to continue to grow. So that's what's happening now. Interestingly enough, the Himalayas, early before we understood plate tectonics, well before the 60s, we had people hiking in the Himalayas, obviously. And people there would actually find seashells preserved in the rocks up really high. Shells that we see in the ocean today. Obviously, this location, there's no ocean anywhere nearby today. It was very curious to geologists and other people. How did the seashells get there? At such high elevations. Basically, this mountain's 30,000 feet high, 29,029 feet at Mount Everest, to be exact. So it's like, how did these shells get up so high? And plate tectonics helped explain that, because when India collided into Asia, this intervening ocean basin got scraped up into the mountain building process, and the seashells, including the coastal zone, got pushed up into this mountain range. And that's the reason we see the seashells there today. And the Himalayas are also made up of a lot of ancient coastal type of sedimentary rocks that have been metamorphosed in the mountain building process. As well. So basically, another thing that plate tectonics has helped explain that was curious before we understood plate motion, which is really, really neat. All right, let's go back to the previous slide now and take a look at the features we find here. So for continent-continent convergence, we have basically extreme topography in the way of very, very tall mountain ranges being built. The Himalayas are our only example of active continent-continent convergence today. Basically, the material is very felsic and buoyant, so because it just wants to float, the collision causes the height of these mountains. Now, as far as other geologic features are concerned, do we have deep to shallow earthquakes? Absolutely. We still have oceanic lithosphere here that's deeper, so you're still going to have the capability of having these deep earthquakes down here, although less likely because there's no movement. They can still happen and do still happen. There's no real volcanism. We have a little bit of melt right at the suture zone shown here, but none of that is making it up to the surface very easily. This is very thick and strong material, this continental lithosphere is. Even though it's buoyant, it's hard for magma to escape it, which is the reason for the ocean-continent convergent boundary volcanic arcs to be very explosive in nature, and we'll talk about that in more detail later. So, so the great majority of earthquakes are shallow, although you can get a few deep ones here and there, and no volcanism. And the biggest feature of all is the very, very high mountain range it's created. All right, let's go ahead and go to the next slide now and take a very quick look at transform boundaries. And again, we'll get into more details about this when we get into the earthquakes module. But I just want to talk about the basics right now. And one of the few examples of the world for a transform boundary happens to sit right here in the Bay Area and along most of California, and that is the San Andreas Fault. Let's go ahead and take a look at the next slide. So first I want to list the features. Again, just very shallow earthquakes only, basically within the thickness of the lithosphere. And that is because of the fact that we don't have subduction at transform plate boundaries. And the features we find along the boundary is very subtle. In fact, so subtle, it wasn't until the 1906 earthquake that we even discovered that there was really a fault running through the Bay Area, because a lot of the earthquakes that had happened prior to our settling in California had been healed. The topography, the geology was easily healed by rain and precipitation and things covering up where the break in the rock had occurred prior. So we actually didn't even know this fault existed until 1906. And then it wasn't until the 1960s when we finally realized we had these plates around our planet that were moving about, that the San Andreas was designated a plate boundary fault. So, so very interesting history along this particular boundary. Let's go ahead and take a look at the map of California and where this San Andreas Fault sits in relation to California. So here you'll see Cape Mendocino. Just south of it is basically where the San Andreas Fault ends, and that's also where subduction begins northward. That area there is a very complex geology, but over time the San Andreas is going to grow and get longer and longer and take over up north. Not in our lifetime. We're talking about over tens of millions of years. But nonetheless, the San Andreas Fault is growing in size. And as far as the rupture is concerned of the 1906 earthquake, it was actually quite long. It actually, its epicenter was right off the San Francisco coastline, actually more specifically off the coast of Daly City. And it ruptured the length of the fault all the way to its northern terminus and all the way south into central California. So it was a very long rupture. The Southern California part of the San Andreas Fault had a very similar rupture in 1857, not as famous as in 1906 because that area was not heavily populated at that time, but actually ruptured through here. It's believed the San Andreas Fault will probably most likely rupture in another big earthquake, more likely in Southern California, unfortunately, than in Northern, although we have a sleeping dragon in California with the Hayward Fault. That's actually overdue for a pretty significant 7 magnitude earthquake, which because that fault sits right underneath the city of Hayward and underneath all the cities of the East Bay for the most part, is a very dangerous fault because of that reason. So we're keeping, as geologists, keeping a very close eye on that area and trying to give out lots of warning and preparation materials to all of the Bay Area in anticipation of this fault rupturing within our lifetime for sure. All right, so this is a transform plate boundary because the movement along it is basically parallel to the fault itself. We call that lateral motion. Instead of the arrows pointing towards each other at this boundary or pointing away from each other at this boundary, notice these arrows are parallel to the boundary, and that's what transform motion is. So we call it a right lateral transform fault because if you were standing out here and looking across the fault, the rock movement is to the right. And that's true if you're sitting on this side of the fault looking this way as well. Everything's moving to the right. So we actually name it a right lateral fault for that reason. All right, so that is the end of the lecture on plate boundaries, specifically convergence and transform. A lot of details here, so it wouldn't hurt to go back and listen to some of it. As you become more familiar, you can soak in some more information that way. And I will see you in the next lecture. Thank you very much.